think we're on part 4 now, so trying to finish up this final unit. There's only these 2 parts of it, but we are still talking about the difference in means, but this is going to be a little bit different because now we're talking about paired data. This was when we went through the unit semester 1 where we talked about matched pairs. So like we'd said, you could pair kid with the highest grade with the kid with the second highest grade and then compare some experiment with what happens with one versus the other. Or we could give you a test while you chew gum, and then I'll give you the same test again, but I won't let you chew gum, and I'll compare you to yourself. But having paired data is the thing here. So sometimes you want to compare means in a setting that involves measuring a quantitative variable twice for the same individual or 2 individuals who are much alike. That's what I was just describing. So in this instance, I'm looking at a researcher who's studying a random sample of identical twins who had been separated and adopted at birth. In each case, one twin, which we'll designate twin A, was adopted by a high-income family, and the other, twin B, by a low-income family. Both twins were given an IQ test as adults, and here were their scores. So we have this sample data, but specifically this for sure is not 2 independent samples of people. So it was random, but we 100% failed this independence test. These groups are very similar. They're identical twins. Yes, there's some differences, but we're looking at an example of paired data. So if we just talk about analyzing paired data, we're talking about analyzing the results of 2 values of the same quantitative variable, in this case IQ scores, for each individual or for each pair of similar individuals. So we're going to be talking about analyzing it, and then we're going to do an inference, creating an interval for the true average difference. So just starting talking about these differences. The graph below, which I had to hand draw in because I don't have a scanner, shows parallel dot plots for these IQ scores. So I just attempted to take this data and throw it onto parallel dot plots. It's not great, but whatever. We can just get an idea of what it looks like. So we could see that those raised in the higher income have a higher average. So the balance point for twin A seems to be here, whereas the balance point for twin B seems to be like, I don't know, here-ish if you're trying to balance it on one finger. So it does seem to be higher for one group as opposed to the other. We can also talk about looking at the variability. I haven't calculated in the notes, but you're talking about how one group seems to be slightly more spread out than the other. But the problem is there's a lot of overlap between these groups. So the difference doesn't seem statistically significant because for a huge chunk of them, they're living in the same zone anyway. Yeah, this has a couple dots outside of that and a couple dots outside, but the overlap seems concerning. By just looking at the parallel dot plots, that's ignoring the fact that these are paired and not independent. So if I looked at just the difference within the pair, we can analyze that. So within the first pair of twins, the difference of high-income family raised and low-income family raised had a difference of 8. The next pair of twins had a difference of 5. We can look at these differences specifically, excuse me, and then display those dot plots. So again, I hand drew mine. After it's been calculated, I have it in here. And most of these, of the 12 differences, 11 of them were positive. Only one didn't have a positive difference, which tells us a lot. It tells us that we have some, I wouldn't say convincing evidence yet, but our evidence is leading us down the path of thinking that identical twins raised in high-income households tend to have a higher IQ score as adults than identical twins raised in low-income households on average. We can quantify then that average difference, which is what this is denoting. It's the sample average of those differences, or the sample average of twin A minus twin B. So I'm just taking those differences, I've summed them all together, and then I divided by 12. So I got 5.833 for that average difference. So we're seeing that the IQ score of the twin in each pair who was raised in the high-income household is 5.83 points higher than the twin in the low-income household on average. We can find the standard deviation here. It's a lot smaller than when we just incorrectly thought of them as completely separate groups. We shouldn't be thinking of them separate because they're not independent. That's what we would want to be doing instead. So that's what example 3 is getting at. We have this matched pairs set here. That's not true. It's not even matched pairs. It's one student who did two different things. So the student, or these student researchers, Abigail, Charmaine, and Jamira, designed an experiment with 30 student volunteers to find out if music helped or hurt math performance. So they completed a 50-question arithmetic test with and without music playing, and the order was randomly assigned. The time to complete the test was recorded for each treatment, and here are the data along with the differences already calculated. So making a dot plot of the difference. Again, you didn't need to watch me do that, but theoretically you are capable of putting these numbers in a dot plot. So that's just what I did. It's not as obvious as the twin study. We don't have dramatically, these are all positive or these are all negative. So we can kind of see it kind of getting split up, positive to negative. Make sure if you were ever asked to create a graph, you label what it is to make it have meaning. But this reveals some stuff about whether music is helping or whether music is hurting. So we do have some evidence that music hinders performance on a math test. It's not great, but it seems like there is some evidence. And that evidence is if we actually count how many took longer to take the test. So, okay, let's talk about the order of this. If it takes you longer when listening to music, so this would be longer than without music, then this order would be something that's positive. So like if it took me 10 minutes, but without music, it only took me 7 minutes because it took me longer with music, I'm getting a positive difference. So if I just count the number of differences that are positive, I can find that 17 of the 30 subjects so a little over half, but I mean, none of them. 17 of the 30 subjects took longer when they're listening to music. So then we do have some evidence. I'd like to then know the mean difference and the standard deviation of the differences and to interpret what that mean actually is standing for. So remember, it's the sample mean difference of the music minus without the music. So the bottom row on the table up above. So I could show my work of doing that, but my textbook doesn't even bother to do that. We get about 2.8 seconds for the average difference. So it is a positive average, again, leading us to think that it's taking people longer on average to do this. The variability, and I just put this in my calculator to find these numbers, by the way. So I got 7.49 seconds. So if I'm interpreting just the mean, that I'm just saying that the time it took these 30 students to complete this quiz with music was 2.8 seconds longer on average than the time it took without music. So because we're talking about an average, we can come up with a confidence interval. We could say, okay, this is what we're estimating it is. This is my point estimate. Let's add and subtract a margin of error so we can try and capture the true difference to see, well, is 0 a plausible value for this? I don't know. This is 2.8. It depends on the margin of error. So let's actually create a confidence interval. So we're creating a confidence interval for the population difference, which is different than what we were just doing before this video started. So when paired data come from a random sample or a randomized experiment, that statistic we were just looking at is the point estimate for the true mean difference. So mu sub diff. So we have sample average difference and the population average difference. Before constructing this, we always have to do those conditions. And aside from the paired data requirement, these are identical from the last section when we just talked about the one sample t interval. So we're going to talk about the random condition. Whoa, that was weird. paired data come from a random sample from the population of interest or from a randomized experiment. You'll notice that it's not saying independent random. Like, that word is very intentionally not in here. This is paired data. It will never be independent. These two groups are linked intrinsically. You still have the 10% condition. This is not a two sample test we're doing. I'm just looking for the number of differences being less than 10% the population of differences. So the number of differences literally means you get your two groups of people, how many differences do I have? So there were 15 on the top row, 15 on the bottom row. There are 30 differences altogether. So 30 students had 30 differences, or you could think there were 12 pairs of twins. So yes, 24 people, but there were only 12 differences. So again, this is not a two sample T interval we're creating. This is just looking at the number of differences and coming up with an interval for this true difference in this paired data. So it's paired data is really important. Still got to check the normal large sample. Remember, it's the large counts conditions if you're talking about a proportion, normal large sample if you're talking about a mean. So still works the same. If the population is normal, specifically the population distribution of the difference or the true distribution of difference in the experimental response of the treatments, or if your sample size is large, which remember is N sub diff, but our threshold is 30. If you don't know and you have a small sample size, then you're just going to have to graph it to look at that. If you met those conditions, you use your formula, the statistic plus or minus critical value times the standard error of the statistic, which looks like this, which should look pretty much identical again to last section. Last section, we instead, oh wait, I think I kind of mixed and matched those. I was intending to show how it was similar to last section. This is actually just a typo. This should be the standard deviation of the differences over the square root of the number of differences. So again, in that twin study, not the fact that there were 24 people in the sample, that there would be 12 differences in this sample. So these are both wrong. My apologies. So again, it's still a one sample T interval because yes, I'm saying one sample, but it's a group of differences. But we have a group, one group. It's a T interval specifically for the mean difference. You could also think of it just as a paired T interval for a mean difference because it comes up when you have paired data. So if we go back to those identical twins, if I want to construct and interpret a 95% confidence interval for the true mean difference in IQ scores for these differently raised twins, four-step process, you gotta start with stating. So I'm gonna state that I'm going to be creating a 95% confidence interval specifically for the mean difference. Again, this is the population, the true mean difference, and then I'm going to specify what order I'm talking. This table had structured it the high income minus the low income. You are welcome to flip those as long as you have defined what you've done. The order is not the answer as long as you communicate it. So it's the difference in IQ scores for pairs of identical twins raised in separate households. So our plan includes what I'm actually creating. And again, this is not two samples. You have paired samples. It's the hard thing to communicate once they start getting mixed together. So one sample T interval for the population mean difference in that paired data. I went ahead and wrote out most of the conditions because you should be getting tired of them by now. We have a random sample of 12 pairs of identical twins, and I specified what those samples were like. I did not put independent because they're for sure not independent. And then we are able to assume that 12 is less than 10% of all pairs of twins raised in separate households. So we have 12 pairs. That's a reasonable assumption. So your normal large sample, we don't have a large sample. It didn't say the population. We don't know anything about the population distribution of twin IQs that were raised in different incomes. So because of that, we're going to have to look at the actual distribution. So if I take all of the differences in the twin data, so it ranged from a -1 up to a 12. 2, 4, 6, 8, 10, 12. I'm surprised I don't already have this done. You get to watch me make a dot plot now. I do need to specify what I'm creating. So this is the difference specifically twin A minus twin B in IQ scores. So I'm just gonna put my values on here. We had 2 1s, 2 5s, 2 6s, 2 8s, a 9, a 10, and a 12. So it's not dramatically skewed. There's no outliers. So even though the number of differences is small, even though the sample size is not at least 30, however, our dot plot isn't showing strong skewness or outliers. Whoa. So we can proceed. We've passed those conditions. So we're actually going to now create our one sample t interval for the average difference. So when I do this, I need to know what the average difference is. So theoretically, in my calculator, I will put in all 12 of those numbers. I'll find the sample average and the sample standard deviation. I've already done this for you, so you can just copy off of me. So the average difference from my calculator the sample standard deviation of these differences is 3.93, and again built off of a sample size of 12. So since I'm at a 95% confidence level, if you go back to that first lesson, you don't use that god-awful formula. You just go ahead and say, sample size is 12. I got 11 degrees of freedom. So I can then find my critical value using inverse t at 95% confidence. My area would be half of 5%. So I'm going to use 2.201. So I'm ready to put all this together into an interval. So I'm going to take our point estimate. I'm going to add and subtract our margin of error. Which would give us so when we conclude, we used a process that makes us 95% confident. We know that we would have a 95% capture rate if we did this sampling over and over and over and over again. So we are 95% confident that the interval from 3.336 to 8.330 captures the true mean. Specifically for this one, it's not just a true mean, it's not just a true difference, it's the true average difference. Specifically of the high income minus low income IQ scores. Pairs of identical twins raised in separate households. So it's suggesting that It's higher on average for twins raised in the high-income households. You can't say that this is a causal relationship. And that's because this was not an experiment. This was an observational study. There was no treatment applied. You didn't say, okay, these babies are being given up. You go to the rich people, you go to the poor people. That's really unethical. They for sure did not do that. And because it's not a controlled experiment, they cannot extrapolate it and say there's a causal relationship. Because these are not independent, it would be not appropriate to use a 2-sample t-interval for mu sub 1 minus mu sub 2. Again, if your data is paired, either 2 observation of the same variable for each individual or 1 observation of a variable for 2 similar individuals, you have to use this 1-sample t-interval for the population average difference. So this will come up again when we start talking about the significance test for the difference in means, but for now, this should be the end of Unit 9. Unit 9, I believe I have on the calendar, will be needed to be completed by April 17th. That is the Khan Academy practices, that is the MyAP practices, and that is the test. I will be linking over the Google form so that you could just answer those questions on there. The only thing that is going in for a correct or incorrect could have impact on your gradeness of it is that test. Wow, that's the word I wanted, is the test. Everything else is just completion credit. But again, that's for those of you going for the Lewis and Clark credit. If you're just like, hey, I just want to have a stats credit on my high school transcript and graduate and get this over with, you just need to do it. Excuse me, so that you have participated in what we have continued to learn about. But the State Board of Education for Illinois is very adamant that your grade, whatever you ended with when I last saw you, March, I think 16th, your grade can't go down below that. It's stuck at that level. That will be the grade bare minimum that you have in the class. It could go up. I haven't looked at any of the extra credit that you might have done. It could possibly go up. It will never go down. That should be true for any of your classes, so make sure you're keeping an eye on that. Teachers cannot make your grade go down. Theoretically, your Lewis and Clark grade could go down, so I'm going to have to figure out how to have a separate grade book for those of you going for that credit, because let's say you get like 10%, let's hope not, but if you get 10% on the next few tests, even though I'm going to have these tests weighted 25%, what a test usually is for this class to take into account the weirdness of all this, even though it's going to be weighted less, if you get a bunch of 10% on there, your grade probably is going to go down because none of you were averaging 10% before this. So your high school grade will be untouched, but your Lewis and Clark grade can still be influenced based off of how you do on these tests. So that's why you need to actually take seriously the Khan Academy practice and the MyAP practice so that you have a hope of not like totally tanking your Lewis and Clark grade. They have sent out information for the drop date for that. I don't have it pulled up in front of me, and I don't want you to have to wait for me to find that, so I'll try and send an email about that later on in life. But if you're thinking that, yeah, you're done, you just want to get high school credit, move on, it's 100% an option to drop the dual credit, to drop the AP test. I think I heard today they're going to send out something more official tomorrow, but it sounds like the AP test might be literally one question for 45 minutes, which seems a little weird. Sorry. But again, when I know more information, I'll try and pass it on to you. When you have questions for me, ask. But finally, Unit 9 is done, and we can start moving forward and eventually go on to Unit 10. So go